Welcome to today's lesson. In this first tutorial, we will have a general introduction to the rational function. So now we are in section 3.3 in our textbooks, and we're looking at rational functions in this little bit of a chapter. A rational function is a function f of x that is equal to p of x divided by q of x. Rational means ratio, so we have the ratio of two polynomial functions, and that ratio is a rational function. Now, since we have a denominator, our denominator, of course, can never be equal to 0. So we're going to be very interested in the values that make the denominator equal to 0. So let's first start by generating a graph for this very basic rational function 1 divided by x. I'm going to put in some tick marks, 1, 2, 3, 4, 5, maybe 5 on each side. Space them out evenly there. A couple tick marks up the y-axis, down the y-axis. Sure. So I'm just going to generate some values just by plugging in whatever I want for x. I'll plug in a 0, I'll plug in some positives, I'll plug in some negatives. So let's start by plugging in a 0. Unfortunately, that's the only number that I cannot plug into this denominator, because like we just said, the denominators can never be equal to 0, so therefore x cannot be equal to 0. We actually have a vertical asymptote right here at x equals 0. So I'm going to dash that in. So that's a number we cannot plug in. Let's plug in a 1. If I plug in a 1, I have 1 divided by 1 as my output, and that is a value of 1. If I plug in a 2, then I have 1 divided by 2 as my output, and that would be 1/2. If I have a 3, then I'd have a 1/3, and then a 1/4, and then a 1/5, and I could keep going smaller and smaller and smaller and smaller, but I will never actually touch the value of 0. I can get a very, very, very tiny fraction, but I will never let it equal to 0. So there's actually a horizontal asymptote right here at y equals 0. The function will never be equal to 0. Now, what if I happen to plug in some values in between 0 and 1? For example, 1/2. If I plug in a 1/2, 1 divided by 1/2 is actually a 2. And if I plug in a 1/3, 1 divided by 1/3 is 3. And 1 divided by 1/4 is 4, and so on and so forth. So you can see that we're infinitely getting closer to the vertical asymptote, and we're also infinitely getting closer to the horizontal asymptote. And that's the first part of this rational function. Now, we're never actually touching this asymptote here or touching this asymptote here, so make sure that your graph does not get sloppy and touch those asymptotes. There's another piece of the graph. What if we start plugging in some negative values? If I plug in a -1, 1 divided by -1 is -1. 1 divided by -2 is -1/2. And then -1/3 and -1/4. So very similar to the points that are over here, except that they're on the negative side. And then similarly, I'm going to plug in the -1/2 and divide by -1/2, and I get a -2, and then a -3 for -1/3, and then a -4, and so on and so forth. So similar to these points, but again on the negative side. We're getting closer to each of the asymptotes, but we're actually not touching them. So this is our basic rational function curve. Now I keep talking about these asymptotes. There's a vertical one and there's a horizontal one. I like to think of an asymptote as a boundary line, sort of like a fence. Maybe a fence. Kind of keeps our function in place. The graph approaches. Now, I know you might have already learned in a previous math class that you should never be touching your asymptotes. That's actually not exactly entirely true. The vertical asymptotes you will absolutely never, ever touch because those are undefined values. Sometimes, though, our horizontal asymptote will be touched, and we'll talk about that when we get to those situations. Let's talk about the domain for this function. The domain is the set of all x values. So since x can be everything except for 0, I'm going to write my domain in a set notation. and I'm going to say it's the set of all x such that x is not equal to 0. That's how I prefer to write domains, usually for rational functions. Some people like to write them in interval notation, and they'll say that the intervals that x could be are from negative infinity to 0, and then from 0 to positive infinity. Either one of those is absolutely fine. As long as you use a correct syntax, it's fine with me. Let's talk about the range. Range is the time when we look up and down on our graph, and the only value that's not listed in our range is the value of 0, this horizontal asymptote. So I could actually write the same exact stuff, of course, except with a different variable, all y, such that y is not equal to 0. Or if you like the interval notation, negative infinity to 0. Remember, we're using a parenthesis on this 0 because we're not including it. And we don't forget our union symbol to union the two intervals together. Let's talk about x-intercept and y-intercept. Well, this graph actually does not have an x-intercept. We never actually touch the x-axis, so therefore our x-intercept doesn't exist. We could say DNE or none. And similarly for the y-intercept, we don't actually touch the y-axis either, so we don't have a y-intercept. Let's talk a little bit more about this graph, in particular the end behavior. What is happening at the very far ends of the graph? As x approaches positive infinity, what's the graph doing? And as x approaches negative infinity, what's the graph doing? Well, actually, both parts or both sides of the graph, both ends of the graph are doing the same exact thing. So from this rational function and most rational functions, I can describe the end behavior by describing both sides at once. As x approaches positive infinity, that's the far right end, and as x approaches negative infinity, that's the far left end. In this case, I need to know the name of the function. It's f of x, okay, so I'll call it f of x. This rational function, f of x, is approaching the value of 0. The right end is trying to get to this x-axis. It's never going to actually touch it, but it's trying to become the value of 0. And the far left end, it's also trying to become the value of 0, of course, from below. This one's coming down from above, and this one's coming up from below, but they're both trying to reach the value of 0. That's the end behavior for this rational function. We also like to talk about, since we have some asymptotes now, we also like to talk about either the middle behavior, or some books might call it the asymptotic behavior. Basically, how is the graph behaving at the asymptote? So we have two different sides. We have one vertical asymptote, and we have two different sides of that vertical asymptote. We have what the graph is doing on the right side, and we have what the graph is doing on the left side. So we actually have a new symbol, and we're going to say as x approaches, now we need the value of this vertical asymptote, which is 0. X equals 0 is the vertical asymptote. So we need to know what's happening as x approaches 0. But like I said, we need to know which side. So we put a little plus sign up in the superscript. It's like sort of in the exponent area. This plus sign means that we're approaching from the right. And as we're approaching from the right, the function, the red part of the curve, or the red curve, is doing something. So if we get to 0 and get on the right side of 0, and then start approaching infinitely closer to the 0 from the right side, you can see that the graph is skyrocketing all the way to positive infinity. And that's what f of x is doing on the right side of the asymptote. On the left side of the asymptote, we have to describe that with the symbol, and we'll use a little negative sign. That means that we're approaching this value from the left side. Let's see if we can follow the graph on the left side. So get to my 0, get on the left side of 0, and then start getting closer and closer and closer to 0 from the left side. And you can see as we do that on the x-axis, the function is going all the way down to negative infinity. So that's our asymptotic behavior. So that's a quick introduction for our rational function and a bunch of the things that we can describe for it. And I'll see you in the next tutorial. Bye-bye.